Alright, so in the third part, we will learn two other basic, and I think that's all the basic operations we need to use when we deal with the vectors. So first, we have the vector norm. So that's just a fancy way to say about the size. We have, since a vector is can be represented as a line between 2 points with an arrowhead on one side, then we can just talk about how long is that line and what's the length of that line. If you use a ruler to measure the line, and the way it works is we use the what we studied last time, the Pythagorean theorem. It says we have to first write the triangle first. And so suppose this is a vector A and B, and if you draw it by putting the initial point at the origin, then the final point or the terminal point will be at the point AB. That means we have this coordinate A there, and also coordinate B there. So the length of this horizontal line and the length of this vertical line are A and B, respectively. And of course, by the Pythagorean theorem, we can find the length of this vector by the c squared equals to a squared plus b squared. And then c is the square root plus and minus square root of a squared plus b squared. But since we talk about the length, so we can get rid of the negative part and define the length to be the positive square root of a squared plus b squared. And we have to make give it some name or some symbol, right? And the way we use it is we use double line. Sometimes you see just a single line on both sides, and that's fine. They mean the same thing. They are measuring the length. And one thing you notice is that it looks pretty similar to a negative value. I mean the way the lines look. Now, if you want to find the negative value of 2, you get 2. If you want to find the absolute value of minus 2, you get 2. Absolute value of 1.5 is 1.5, and so on and so forth. And actually, these two notations are the same notation. It's kind of strange how you call a notation for numbers in one name and call the same notation in vectors for another name. Because if you go back and look at the real line, you have 0 in the middle. So if you have a point minus 3, you want to find the absolute value of minus 3, and that's the same as the distance or the length from that minus 3 to 0. So it's this length. That's why we get 3. And you can see that the length is the same as the vector. And because this line from 0 to 3 has length 3. If you don't care about the order, which is first, which is second, and that is a line of length 3. And for the top positive value to point through, then the length is just that number, just at that point. So absolute value is the same as the vector norm. That's the reason why you need to write them in using similar notations, using vertical lines for both cases. And then for the vector, since we have a plane, we have both x and y, then we need a way to measure the length using the Pythagorean theorem. That's all we have, and there's nothing more for now, for this moment. This is the exercise, but let me just show you an example. For example, this vector 0, 2. So 0 means you don't move, like 2 means you go to the coordinate of 2 in the y-axis. So this pink vector is this vector 0, 2. If you give you this image and ask you for the length, you can just say it's 2. It's 2 steps up. 2 steps up straight. No left or right movement. So the length is 2. The way we use this notation is the length of this vector, or the norm of this vector, is 2. This will be the full notation. If you happen to give it a name, let's say V, and also say the size of V is that, which is 2. So if you use a formula, it's the square root of 0 squared plus 2 squared, which is square root of 4, which is 2. As simple as that. Oh, I didn't mention one thing. If what happens if you have negative value? Because you don't have negative size, right? You cannot measure the length of size negative. But if you draw the image of this vector -1, -2, and 1, -2 it means you go there, 1 you go there. So this is the vector. This is a vector v equals 2, -2, and 1. And if you want to measure the length, then you don't use negative value. You use the side of this triangle. And this side had length 2. It's not -2, it's 2. And the vertical side, it's -2, -1. They are both negative. Oh, let me stick with this example. -2 and +1. -2, that's 1. And when you think about the side length, like not the value itself, so you use these numbers to find this size by Pythagoras theorem. And the nice thing about this formula, maybe it's coincident, I don't know, is that since you use the square, right, then even if you have a negative value, then you can still put a negative value in the formula. And that will give you the positive value. And that will happen to be the same as like this sine square. So that means you can plug in the negative value into the formula for the norm, or for the side length of the vector. And so that's the norm. And the norm itself is fine, right? But maybe you might get confused when we like have some notations around. For instance, if I ask you to find the norm of the sum of these two vectors, is it the same as the norm of these two vectors added together? Think about it. Is it true? It could be true sometimes, but not always. Because you can think of if you actually draw it out. Let's say that's v, that's u. This would be the sum u plus v, v plus u. And this equation claims that the sum of these two sides, like yellow and blue, is the same as the pink one. Which if you think about it visually, like if you try to rotate this v like to lie on this one, and then you to next one, you can see that it actually peaks. It peaks out of the vector u. Right. So in this sense, it's not the same. You can even say more about this one. If you have a triangle, if you have like 3 sticks and you play around with those sticks, right, this triangle also says that it's not equal, of course, but we can say something at least about this relationship between these 3 lines, these 3 vectors. If you choose that the sum of these two, like this yellow and blue line combined, should be at least it is greater than or equals to the norm of the sum of the vector. Again, you can think of it physically. Like if this pink represents walking like the shortest distance from one point to another. Like, since it's the shortest distance, if you go to anywhere else and then come back to the destination, like that distance combined should be higher than the shortest distance. And so this inequality makes sense. So they are not equal, but we can at least say they are less than or equals. And since they are less than or equals, can you see what happens when they are equal? What's the case? It's the case when u and v Let's think about it. Can you make a triangle where the sum of two sides is the same as the third side? Let's say if you have two pens of the same size, can you make the third side to be 2 times that? And yes, of course they can. What happens there is that this happens, they are equal. When V and U are parallel. Oh, sorry, V and U are not parallel, V and U are. Oh, there are actually two properties, right? They are parallel and have the same direction. Parallel and have the same direction. So why do we need two properties? Right? Why is it not just one? Because if you think about it, if let's say we just have the two copies of the same vector this way, and then the sum will just be just over these two vectors. And so in this case, it is clear that the sum of the yellow line and the blue line, the yellow vector and the blue vector is the same as the pink vector. So this works, and this seems to be the only way it works. And so of course they need to be a parallel. And why do it need to be the same direction? Because if you have V here and U points to the back, let's say that's U, then the sum is only this length. It's V plus U. And you can see that this sum is now smaller, even smaller. And so this could happen. But it's not always true. Like it's not the same as adding two numbers where you can split them out. You have to make sure you can imagine what is going on here and see what are the exceptions, the truth, the inequalities, the relationship between two different objects. So they are not the same. And then if you ask me how to compute them, then of course just do it one at a time. Just like if you want to compute 3 plus 4 to the 5th, then you would just add them first, right? To get 7 to the 5th. And use your favorite calculator to get the result. I don't know. I don't memorize 7 to the 5th. But for vectors, let's say I want you to find. If I want you to find, let's say, if I have U equals to 1 and 4, V equals to 4 and 2. And then the length of the sum, you just first find the sum. It'll be 1, 4 plus 4, 2. Then let's find the sum first, like 1 plus 4, 1 plus 4 and 4 plus 2. It gives you 5 and 6. That's the sum. And then to find the length, you just use the formula 5 squared plus 6 squared. It should give you 25 plus 36 or 61. And so that's the length of this vector. We draw a graph. 1, 4 is moving like that. 4, 2 is going in that direction. So that's the result. That's the total. The length of this green line, of this green vector, is square root of 61. And if I can ask you to find the difference, then just do it. Yes. I just find the difference first. Yeah, this will be 1 minus 4 and 4 minus 2. And this gives you minus 3 and 2. Is square root of minus 3 square plus 2 square. Square root of my plus 3, which is square root of 13. That's the length of the difference. Erase that. Which you can see right away that they are shorter. maybe it's not clear from the numbers themselves. But if you do the math, then you can see they are shorter. So again, if you want to find, let me you want to find u minus v. If you want to visualize u minus v, I suggest you visualize u plus minus v instead. So if v is that direction, then minus v is in that direction. So you flip it, minus v. And that's the sum of those two. Is this purple vector. U plus minus v. And again, if you look at the image and compare the numbers, it makes sense, right? This purple vector seems a lot shorter than the green vector. So it makes sense that the length or the norm is smaller. And so that's the norm. And then we have the final basis operation is the dot product, which I mentioned. Actually, the dot product comes from of the angle or the projection. But usually when you in classes, in this class, we first define the dot product to be this dot. And this kind of the first intuition if you ask you to multiply two objects that you don't know anything about. If I give you the two lists of numbers 2 and 3 and 1 and 5, and then ask you, hey, please multiply this for me, you would say, oh, I guess you just multiply it one by one. So it's 2 times 1 and 3 times 5. That's what you would have guessed. But the thing about this is, it's not the result is not a vector. And notice that there's no vector notation anymore. There's no sharp bracket. There's no arrow on top. So that means this has become a scalar. This is a scalar. It's just a single number. So this product, the dot product, and the way we read it, we read this dot as, guess what? Dot. So we just read v dot w. Vector v dot vector w. And the result is you multiply them point-wise, component-wise. Multiply x to x, multiply y to y. Oh, I think I made a mistake. Oh no, it's fine. And we add them up. So in this case, if you multiply if you have the vector v as 2 times 3 and vector w as 1 times 5, then the result is 2 times 1 plus 3 times 5. So v dot u is this number, is it scalar? Is 2 plus 15 or 17? You get 17. Good enough. But you may ask why can't we justify it this way? Why can't we make it of another vector? And the answer is this vector doesn't have any interesting interpretation. It's not that we cannot define. Of course you can define, but the result doesn't tell you anything much about the vectors. For instance, if I let's just simply use 1 3 and 2 2 for the sense. If you multiply them together, what you get is 1 times 2. Let me make it obvious that it's not a good definition. 2 and 3, and then let's say this is 4 and 2. If you try to multiply it in this way, you would get what? 2 times 4 is 8. 3 times 3 is 9. So it's 8 and 9. Why is 8 and 9? On this scale, it goes there. And what is that? What is that vector? What is that? What is that ugly vector? It seems like something totally different, isn't it? And because again, if you think about this as an object, you want to move around and scale it up or down or achieve it, then this doesn't seem like the result of doing these two operations, of performing these two vectors. Just somewhere far away. And unlike the numbers, like because if you have 2 and 3, and these two numbers, then you can interpret the product as the area of a triangle. That should give you the area, right? That'll be more meaningful. This purple vector doesn't give you that, so we don't use it. We don't define it this way because it doesn't have any physical or any proper interpretation. But if you want to find an area, because it's there, right? If you just zoom it in, there is there. Is there a way to find an area? The answer is yes. But you can approach this in two ways. First, you can. I believe there was a formula in high school. I remember for some reason they taught it in like grade 6. That you like make a point, repeat the point and multiply it down and up or something. There was a way to find the area. And the second way is to use interestingly, use the cross product. Use the author product that we don't use in this class. So if you want to describe the area of that parallelogram, you need to use the cross product to compute the exact area of that shape. So it's not a dot product, of course. That's why we don't define them this way. So that's a dot product, and dot product appears everywhere, even if you don't expect it. And one simple properties or one simple interpretation of a dot product is you can find the angle between two vectors, which is another important aspect. Whenever you deal with this kind of movements or transformations, you are almost always want to find the angle. Because at the very least, you want to see whether they are close together or whether they are going in the opposite directions. At the very least, that's a rough comparison. And further, you may want to find whether two vectors are perpendicular. Of course, perpendicular vectors are nice to work with. So you want to know when is that angle 90 degrees. The formula involves two different aspects. Again, interestingly, it involves a dot product and it involves a norm, a size of a vector. The way you compute, you cannot compute theta directly. I mean, you can, but it is the formula is easier to remember if you remember it in terms of cosine. Cosine of that angle is v dot u over the size of v times the size of u, the norm of v times the norm of u. So what you do is given v and u in the problem, you find v dot u, you find the norm of v, find the norm of u, and then multiply them and divide them in this way. Then you can find the cosine of that angle. And then if you want to find the angle itself, then you need to apply the arc cos, like the inverse of cosine, which I mentioned briefly. If you just want to know to know which buttons to put on the calculator to compute this angle, then it is arc cos. The arc cos of this result of the dot divided by the size of v times the size of u. And again, if you just look at this theorem, it doesn't make sense, isn't it? Because why can you like multiply it component wise, and why do you have to divide by the size? Before we go into the computational part, which should be short and simple, let's discuss about this formula. Why would this formula work in the first place? Let me copy there. V dot u over size of v times size of u. How this formula works in the first place. So for instance, first you have to know that you have to know some facts about cosine. That cosine is positive when, if you go back to the trigonometry, the cosine, what is cosine? Is it x or y? Cosine is x, the x value, and so x value is positive here, in the right part of the y-axis. If you know the word, it's the first quadrant and the fourth quadrant. Anyway, it is positive there. And so cosine positive when the angle is small enough. So in this case, let's say if u is here and v is there, then theta, the angle between these two vectors are there. Oh, and we have to put one vector on the positive x direction. So that's that. And let's see if that makes sense. Well, actually, that makes sense, right? Because in this image, right, if you just look at it, just for the sign, plus or minus, you can see that everything is a plus. X and y here are pluses. X and y there are pluses. So the dot product is obviously a plus. So that works, right? And then if we, what happens when, how do we know if cosine is negative? It's negative is, again, the x value is negative. Okay, so that means the other vector has to be on the left quadrant. And what happens here in the left quadrant? You see that for you, again, it's both positive. Actually, it's positive and 0. If you rotate it this way. But then for v, what happens with v? The x value is negative, while the y value is still positive. So the product, like the dot product, you have positive times negative for the first. And then you add that to 0 times positive. So that's how you get a negative value. So we can see that this dot product makes some sense. If you fix one vector to be the positive direction, like to point to the right, then the dot product is positive if v is close to u. If the angle is small enough, in this case, it's smaller than 90 degrees. So it's positive when the angle is smaller than 90 degrees, and it's negative is the angle is larger than 90 degrees. We can make some comparison with the other two quadrants as well. But all in all, like this makes some sense. If you just want to know whether if you simply want to know if the angle is between 0 and 90, or is it between 90 and 180, then this formula kind of works. You just take the product of the first components together, and they kind of work this way. Oh, and then you have to know like the rotation stuff, and to prove that that also works. If you is in direction, then if v is like close enough, and then the angle would be, if the angle is small enough, then the dot product of these two vectors is positive. And there's a way to specify that. But anyway, that's just a glimpse of why this works in the first place. And why do we have to divide it by the size? Well, because if we don't, right, notice that the numbers will just blow up forever. If you have two vectors that have some angle theta, and if you just increase the size, like by scale some vector up, then you can see that the dot product also increase. Because if you have a b dot cd, that's the original vector. Let's say the other one is a b dot k times c and k times d. you can see, you can expand and maybe prove something about it, that it is actually k times the original dot product if you expand it out. So the dot product would be higher and higher, which again doesn't make sense in terms of like angle, because if you increase just the length, the angle shouldn't change at all. And so that's one intuition of why make sure we divide by the angle. And lastly, this is the proof, which I think it should come last, because we need to understand each component first. Like the proof is kind of, let's say you have V there, and then you have U here. And the point is, the point is you can split that into two actually. You can think of this as V divided by the length of V. You know it as U divided by the length of U. And oh, I think I haven't mentioned it yet. I will mention this, but this is what we call the unit vector. Because sometimes you have a vector, but you don't care about the size. You only care about its direction. So you want to find a way to extract just the direction of it. And it's kind of intuitive, right? If you have a vector and you don't care about the size, what you do is you divide the size, and the size is gone. But once the size is gone, then we can see that the result. And let's say if the original size is 2, and if you divide it by 2, you get a vector of length 1. If you have a vector that has length 1.5, if you divide it by 1.5, you will get a vector of length 1. If you divide the vector by its size, then the result would be the vector in the same direction, but smaller or shorter. And yeah, that's the unit vector. So what we're doing here is we shrink, like we make a new vector. Let's say we prime, or we dot, because the prime symbol is difficult to see. Let me remove that. And then you can also shrink that to be a unit vector. So that become U dot. And then to find the angle, we need to kind of draw, you guess what? A right triangle of some sort. And then once we have this right triangle, then you can do some math and see that it's about using the side length. Okay, so that's one application of the dot product. Yeah, to measure the angles between two vectors. But let me give you one short example. And this is an interesting example. So suppose U is 1 and 3, and V is 3 and 1. Maybe it's not this one. A is 2 and 1. So if you draw it here, 1, 2, 3, 1, 2, 3, you get this vector. This would be U, because we walk one step to the right, 1 in the first component, and then 3 steps up. It's 3 in the second component. Then we have V here. Now you want to find this angle. Can you guess from the image what that angle should be? Just guess. You think it's 30, 45, 60? Which one? It looks like 45, isn't it? If you draw it using the correct scale, it looks like 45. If you rotate your head a little bit, is it 45? That's the question. And you can answer that using the formula, which is there to find the cosine of that angle. It's the same as you find the dot product. Let me write V first. I think the formula I wrote is V first, then U second, but it should be easy to see that the dot product is metric. These were the same, because if you have A and B and C and D, if you take a dot product in this order, you have AC plus BD. But if you take a dot product in the other order, you get C times A plus D times B, which should be clear that they are the same. So we have here, like we want to find this angle, this nice angle. The way we achieve is we first find the result on the right first. And we can find that by just, maybe it's better if you just write it first, like you find each component first. Like what is the dot product? What is the size of the norm of each of these vectors? The dot product is, now let me write, if I use, yeah, that's pink. And that's blue, 3 and 1. For the dot product, you take the first component, you put together, and then you add that by the second component, you put together. It gives you what? 3 plus 3 is just 6. Oh, it's not 45. It's not 45, my bad. It is 60. But anyway, oh, it's not even 60. It's close to 45. I think it's 37. 53 each. Oh yeah, actually 53 is closer to 60 than 45. Yeah, my bad. But let me finish that. That's 6. Okay, so 6 is gonna be on the top, on the numerator. Okay, it's gone. That's 6. And then what are the norm? Like for you it's 1 square plus 3 square. It gives you what? Order of 10. So we leave it there for a moment. For v we have 3 square plus 1 square, which is again square root of 10. And so what we have here is 6 over square root of 10 times square root of 10. And by the property of the square root, it is 10. Actually, by the definition of the square root, it's 3 over 5. So cosine of that angle is 3 over 5. And if you want to find the exact value of this angle, you can use the inverse function and say, okay, that angle is a cosine of 3 over 5. Let me see if I can use this math. Oh, I can. That doesn't feel right. I think it's the radian or something. Yeah, it's in radian. Yeah, my bad. It's in radian. So we have to multiply that by 180. 3 and 180. Doesn't seem right either. Anyway, you can find a cosine if you put it. It needs to be in the correct scale. That's a cos. But usually when you compute, usually when you want to measure the angle, you are going to use that angle to measure sine, cosine, tangent anyway. So you rarely need to use it as cos. You can just stick it with cosine. That angle is 3 over 5. And then you can find sine and you can find tangent. If you remember what we did last time. Like for example, we can use the property that sine square is square root of 1 minus cosine square. And so on and so forth. So So that's how you find an angle, cosine of that angle. So that's that's all we need to know for the basic course. To reiterate again, we have plus, we have minus, which you can get rid of that and think of it as plus times minus. That's easier to visualize. Then we can multiply it by a scalar, multiply it by a number to scale, to shrink, or to flip, to reverse the vector. You can find the size of the vector, and then you can find a dot product of two vectors. And so now these are the 5 transformations. Oh, sorry, 5 operations, 5 basic operations that we need to know. And then for not this class, but for I think it's week 14, we will see how we can compute and how can we use these vectors operations to actually perform the rotation of dots or of shapes on the plane. And yeah, I think it's a good time to stop. So